This is a second video on rational inequalities intended to follow the first introductory video. We have already established that zeros of the numerator and zeros of the denominator are all boundary values in a rational inequality. So what we're going to do is figure out what those zeros are. From the factor x, if I set it equal to 0, I immediately get x equals 0. If I set x minus 2 equal to 0, I get x equals 2. And x plus 1 squared, the square has no effect on what the zeros are themselves. There are simply two factors that are identical, each of them equal to x plus 1, and each of them would have the 0, x minus 1. So I have three boundary numbers, and I'm going to mark all three of these on a number line. Making sure to put them in order. -1 is the smallest number, 0 is in the middle, and +2 is on the right. Now I am going to do a sign analysis, and for this I will select representative numbers from each interval. Anything to the left of -1 will do here, so I'll pick -2. Anything between -1 and 0 would work, so I will choose -1/2. Anything between 0 and 2, I will choose 1, and anything to the right of 2, so I'll choose +3. I'm going to now do a sign analysis. In preparation for this sign analysis, I might observe that the squared factor can't influence the sign of this whole expression. This squared factor is always positive. The only time it's not positive is when it's equal to 0, which occurs only at x equals -1, which is not going to be in the interior of any of my intervals. So it's sufficient to just look at the factors that aren't squared, x times x minus 2. So I've written x times x minus 2 into my table, which I'll use for the sign analysis. Before I start, I'm going to also mark up my number line with solid and open circles. -1 is the only number that is not in the domain because it came from the denominator. The zeros of the denominator are boundary values, but they are never part of the solution set because they're not in the domain. The zeros of the numerator, those are the ones where I have to look at the type of inequality. We have an inclusive inequality, which means that the zeros are part of the solution set, and that's why I'm going to go ahead and put solid dots at 0 and 2. This way I won't have to think about that part later when it comes time to make the bracket types. Okay, so my x values that I'm going to test are -2, -1/2, 1, and 3, and I've already determined that I can just look at the non-squared factors for the sign analysis. The factor x is negative, the factor x minus 2 is negative, and therefore we have a positive product. At x equals -1/2, both of these are negative again. I still have a positive product. At x equals 1, we have positive times negative, which is overall negative. And at x equals 3, both factors are positive, which means the overall sign is positive. So my sign pattern goes plus, plus, minus, plus. Note that it makes sense that the one boundary value over which we did not change sign was the one that corresponds to the squared factor, right? If we have a squared factor, that one usually doesn't affect the sign, and therefore we don't see a sign change across it. Now, the other thing that we need to do is determine whether we're including negative or positive intervals in our solution set. Numbers that are greater than 0 are positive, and therefore the intervals over which this function is positive are the ones I want to include. Now I'll go ahead and think about the bracket type. Here where I include these zeros, I will have square brackets. Here at -1, where I don't want to include this in my solution set, I have to have round parentheses, even though I come right up to -1 on both sides. -1 itself is not part of my solution set. So I start at -infinity, come up to -1, start over again at -1, come up to 0, start over again at +2, and go up to +infinity. This is my solution set. This next inequality is a little bit more difficult because instead of having, so because we don't have a 0 on one side this time, we can't find the zeros of the numerator and the denominator just by starting with this rational expression. So we're going to have to subtract 3 from both sides, but it's going to get a little more complicated than that because we will have to also find a common denominator. I need this whole thing to be one rational expression before I can find the zeros of the numerator. So I'm going to put this over a common denominator by taking that 3 term and maybe calling it a 3/1 and multiplying it top and bottom by this denominator of my other expression. So I will take the whole -3, distribute it into the numerator here, and I'll end up with the same denominator. So that's going to look like this: 2 minus 3 times 5 minus x in the numerator, and we have the same denominator in both terms now, so just 5 minus x in the denominator. So 2 minus 15 plus 3x is what I now have in my numerator. And 5 minus x in the denominator. Let's bring this up over here and simplify it just one last time. Sorry, that's a plus 3x here in the numerator. So that is now 3x minus 13 in the numerator and 5 minus x in the denominator. And the inequality is greater than 0. So I'm now ready to find zeros of the numerator and zeros of the denominator to mark up the boundary numbers on my number line. The numerator gives me x equals 13/3, and the denominator gets me x equals 5. If you don't see it right away, just set 5 minus x equal to 0. We could solve this by adding x to both sides. We can see pretty quickly that we end up with 5 equals x. So I'll draw my number line and mark these two boundary values. 13/3 is just a little bit bigger than 4. So that's going to be on the left, and 5 is on the right. Now this will divide up the number line into intervals. And now I'm going to pick a representative value from each interval. To the left of 13/3, I can just pick 0. Between these two is a little bit challenging because 13/3 is the same as 4 1/3. So this is actually meaning that we're going to have to take a number between 4 1/3 and 5. Let's take 4 1/2 or 4.5, and to the right of 5, let's take 6. And now let's analyze the signs of each of these intervals. If x is 0, I'm going to have a negative factor on top and a positive factor on the bottom, which means that the overall sign is negative. If x is 4 1/2, so it's a little bit bigger than 4 1/3, my 3x minus 13 is going to come out to be positive, but 5 minus x is still going to be positive, and so my ratio is going to be overall positive. If x is 6, that numerator is now going to be positive, and the denominator is going to be negative. So that ratio is going to give me a value that is negative. Now it's time to look back at this form of the inequality again. This is the same form that I used to mark up my number line. So this is the one I should look at to determine whether I want positive or negative values. Numbers that are greater than 0 are positive, which means that from my number line, I am going to choose the positive interval. And I want to include 3/13. Oh no, I don't want to include anything this time because we have a strict inequality. Those strict inequalities are a little bit easier because we don't have to make the distinction between zeros of the function and numbers that are not in the domain of the function. So this final solution set is just going to use parentheses and go from 13/3 up to 5.